In atomic spectroscopy, we often have samples that have very complex matrices, and matrices that can have other interferences and other effects on our sample quality and results that we wouldn't otherwise have if we just had our element standards in a separate matrix solution. And because these matrices are really hard to replicate, then our standards won't represent our samples nearly as well as in other forms of spectroscopy that we've talked about in this course. So one of the things that is often done with atomic spectroscopic methods is we're going to use a different kind of calibration method. So not just using external calibration, but rather using a method of standard additions wherein we don't have to try to replicate artificially a very complex matrix. We can actually use the matrix that we already have with our sample in it and add the standard directly to that, so that way we aren't we aren't having to replicate the matrix. It's just using the same matrix that the sample's already in. Now, the next video in this that's posted on Blackboard will show you a method of standard additions using multiple solutions, but in some cases we don't have a lot of our sample, and so when we're sample limited we don't want to have to use a lot of solutions, and so we're going to do this one using a single solution. So what does this look like in terms of an experiment design? So when you have your sample in a container, right, you're going to have some volume of the sample, okay? And what we're going to do is we're going to kind of iteratively add some standard to it. So we'll add a small amount of standard and mix it up, and then we would add another bit of standard and mix it up. And we would take the intensity initially. So we would kind of measure our result of the standard initially, and then we would measure the intensity, intensity of the sample initially, but then we would measure the intensity of this sample mixed with standard. We're going to have the standard plus the sample, and we would take that intensity. Then we would add additional standard and take this intensity. Okay, and so along the way we would plot, ideally, we would plot just the intensity change as a function of the amount of standard used. But the problem here is that the intensity is more correlative to a concentration, and we're changing the concentration not just by adding standard, but the total volume is also changing. So we're going to have to do a little bit more, a few calculations in order to set this up and see what we need to graph in order to have a linear response to some kind of a unit that includes concentration. Okay, so let's take a walk through how we might do this. Okay, so as an example, let's say I have an unknown sample that we just don't know what the concentration is. But I'm adding a standard, and I'm going to make this standard at a concentration initially. So the standard solution that I'm adding is, let's just say 2.5 molar. Okay. Let's say I start with a volume of my sample that's 50 milliliters. And each time I add the standard to this, I add some volume of standard. Let's say I'm going to add 2 mils each time. So at the initial point, I'm adding nothing because I'm going to take a measurement of the intensity of the sample alone. We'll just say, we'll make up a number 346. Okay. So initially I have no sample added, and so I don't actually have a sample plus standard. It would measure the same thing. as just the sample because there's no extra standard in there. Okay. But so I take that first 50 mils of sample that has no standard in it, and I'm going to add 2 mils of standard to it. I now have a total volume, I'm just going to use red here for this again, a total volume, instead of 50 mils, I now have 52 mils because I've added 2 mils of sample. Now in all these cases, what we want to know is what is the concentration of our sample initially, and we just don't know that. That's what we're trying to find out. But in the case where we have added some volume, we're actually changing our final concentration from the sample, right? So anytime you're adding volume to a known concentration of something, we're going to ultimately have decreased the concentration. We increase the volume, decrease the concentration. So our final concentration from the sample, from the starting 50 mils, is whatever concentration we had initially times that change in volume, right? We had 50 mils of this starting concentration. Now we're into 52 mils. And we get this just from, C1V1 equals C2V2. Okay, so I just rearrange this equation to solve for essentially a C2. We have C1 V1 over V2, right? So our initial of just the sample, this doesn't change our initial intensity. This is a measurement from the computer or from the instrument. But then if we take this whole solution with the standard and kind of mix it up, now we're going to have a higher signal because we've added some of our standard. This is exactly the element that we're looking for, and so we see an increase in signal because we've added some of that element. Now we know how much we added and we know what we started with on that, and so let's indicate, I'm going to change colors to green here, what our final concentration is of the standard, right? We added 0 standard in the first one, but in the second one we had 2 mils times 2.5 molar divided by a new 52 mils. And this is the same thing, we're using C1V1 equals C2V2 in order to get that value. Okay? But what this is ultimately saying is that whatever volume change we're using and whatever starting concentration we're using, we can use that to end up calculating our final concentration. So this is for after the first addition. Now if we do more than one of these additions, then we'll just like expand the table down, right? We'll always keep 50 mils. We're going to increase our volume of sample by 2 mils each time. So our total volume increases by 2 mils each time. We still don't know what this is, but we're going to use kind of the same process for the rest of these. Okay, and whatever instrument measurement we get is the instrument measurement we get. So as we go, what values are changing? Our volume of the standard is changing, our volume of the solution is changing. These concentrations will change based on the volumes, and this measured value will change for the instrument. Okay, so as we think about what kinds of things we're doing here, if we start to write some of these equations out where we put kind of everything in terms of these volumes and our concentration that we want to know and our end observed value, we're going to write an equation and kind of derive an equation here that we can graph using the values that we've got in this table. Okay, so in this case, this is the same value every time. It's not changing. These ones we know how it's changing. I changed colors there on accident. V is simply the sum of V naught plus Vs, right? We can agree that that's how we get that number. This total volume is the same as our initial sample plus our standard. Xi we don't know, but our concentration of X after we've added some amount of standard is always going to equal the initial concentration times the volume initially divided by the new total volume. Okay, that's always going to be XF. And similarly, our concentration of standard is going to be our concentration of standard initially times the volume of standard divided by the new total volume. Okay. So these are going to be important here in a bit. Okay, so in general, what we're looking at is how is our intensity changing as we're changing our sample that we're measuring, our solution that we're measuring. So we're going to build a proportion here. We know that concentration and intensity of signal are directly proportional, right? So we know that for the concentration of our analyte in our initial sample is going to be proportional to that initial measurement of intensity. But then later on, what we also know is that we can build a similar proportion to after we've added the standard. The intensity that we see is going to be due to the concentration of our analyte that was initially now diluted. Okay, so this is our analyte present in the initial sample that's now been diluted, plus our standard that we've added that has also been diluted. Okay, so this SF, concentration SF. And so if we know that these two are proportional and these two are proportional, then all I'm going to do is make this all one big proportion. And we have a starting equation with which to work with. Now, this is a great start, but as we've already established, some of these values are changing with volume. So what I'm going to do is just substitute in for XF and for SF, and we're going to do some rearranging of the equation. So I'll just go ahead and write this out and do a little bit of math here. Okay, so SF, we said this we're going to replace with SI times our volume final or volume standard over our total volume. XF we're going to replace with our concentration X initially, our initial volume over the total volume. Okay, so that's that step. And we're ultimately going to want to plot this measured value on the y-axis. That would be nice, or some kind of derivation of that. So as I'm going to go through this, I'm going to ultimately want this in a numerator on one side, perhaps with some other values, and I'm going to want to put volumes on the opposite side because we want to see how intensity is changing as we're adding volumes of standard, because those are the things that are changing in our experiment. Okay, so as I keep deriving things, what I'm going to do is I'm going to take my new denominator and multiply it by both sides, and take this denominator and multiply it by both sides as well. So I have, if I multiply IS plus X by both sides, I now have this times my initial concentration. And on the other side, I have IX times what's in this denominator, which is concentration X initially, initial volume, total volume, plus concentration of standard initially, the volume of standard added over the total volume. Okay, so there's that one. I can distribute IX to both pieces, So put it both here and here. Okay. I'm just distributing it through. And so now I see I have two fractions here that have volume on the bottom. Working with fractions is perhaps not as ideal right now. So I'm going to multiply through by total volume. So I'm going to have I x s plus x concentration I initially times V equals Ix concentration Xi V naught Ix Si Vs. All right. All right, next step I'm going to do is I'm going to divide everything by concentration of X initially. And so these cancel, those cancel. Okay. And the next thing I'm going to do is actually divide everything by V naught. And I'll show you how this works out in a second, okay? So trust me on this. We're getting to a good point here. It looks a little nuts, but I'm going to divide through everything by V naught and get those two off as well. Okay, so what does this leave us with? Is plus X, our total volume divided by our starting volume. And I'm going to write this a little bit differently. Ix. So as I rewrite this, I'm just going to swap the order of these two here. And so I then have Ix, and we'll put this Xi in the bottom, this initial concentration of X, times Si, and then this volume is standard, volume initially. And then my last term is Ix. So I just swapped the order that I wrote these two in and then kind of broke this up into some different parentheses. Okay, so what I want to point out here is we now have values that change, y, including a measured value here. And we have it in terms of our kind of end piece that is also changing here with this end concentration of our standard. Okay, so as our standard is changing, how is our instrument response changing? And so if we put this value on the y and this value on the x, we now have an m and a b, and we take the form of an equation of a line. Okay, so as I write or draw my, put my data on a plot, on the x-axis, we're going to put Si Vs over V naught. So this is a calculated value, all things that we know, right? We selected what volumes we were using, we selected what initial concentration we were using, and then we have this change in volume that we know times our measured instrument response at each mixed solution. And we get some kind of a value or some kind of a line based on our data that might look like this. We do a best fit line here. Now if we use the equation of the line, we can actually work backwards to predict the x-intercept, and this x-intercept ultimately equals negative xi. And so it doesn't perhaps look really simple in the derivation here, but the end result is to get this plot that gives you a linear plot where you can very quickly determine what your x-intercept is and get off of that plot then your concentration of your sample initially. Okay, So let's recap here. We got lost in the math a bit throughout because the math was hard. But what we have here is a setup where we start with a sample and we're adding small amounts of standard to the sample, mixing it up, and recording the instrument intensity along the way. At the end, when we plot the concentration of our standard as a initially times the volume of standard as it changed throughout our experiment, divided by our starting volume of sample, we got a plot here on the x-axis that we correlated with our instrument response at each point in this particular experiment. If we plot it with instrument response times total volume divided by starting volume, our x-axis ends up being a negative or the opposite value of our initial concentration. And that's what we ultimately wanted to know here. So it's a lot of math to get there, but it's important to know where this math comes from, and it all starts from this relationship of correlating concentration to observed intensity. Okay, so this is one method of standard additions. There's another method of standard additions where instead of using a single solution, you'd use multiple solutions, and the math here in the derivation is quite a bit easier. And you'll see that in the Jove video that's attached on Blackboard.